Hello everyone. Right now I will present a paper with title Time Over Attention Based Transformer for Cloud Computing System Failure Prediction. This paper is published at KTB in 2024, and this work is a collaboration between Alibaba Cloud and Huazhong University. So, for the problem that this paper wants to solve are, in cloud experiments, server failures can disrupt thousands of virtual machines. System logs, especially exceptions, contain early clues of this failure. But most prediction models ignore a feature called timestamps. These timestamps are often can reflect the urgency of anomalies. So the challenge is, how can we incorporate both what happened and when it happened? Our motivation is, first, different failures have different exceptions patterns. For example, memory issues look different from disk failures. Second, the timing matters. 100 exception in 5 minutes is more critical than the same number of 3 days. Therefore, we need a model that truly learns from semantic patterns and also their temporal context. This is an overview of our model TAAT. It consists of 5 main components. One is assertion embedding, time embedding, time relation estimation, multi-thread time over attention or MTAA, and also five classifier. In the next labs, we will look further for each component. First, for the assertion embedding, it converts its tokenized flag into a vector, just like word embeddings in NLP. But we will grouping the log first before we tokenize. Like in this image, the similar log will have some exception ID. And then for the timestamp embedding, it will break its timestamp into a day, hour, minute, and second. It giving the model a capability to understand the temporal patterns. So the model will not only understand what occurs, but also when the exception occurs. And then for the three component TRE. TRE computes the temporal or time correlation between every logs, using multi-head attention on timestamps. It learning how exception timing impacts risk. For example, the 100 errors in 5 minutes is not same with 100 errors in 3 days. Then for the fourth component is the multi-head time over attention. This is actually the extend standard transformer attention. They want to integrating the semantic and also the temporal attention scores. And then for the last component is there is a class or token that summarizes the sequence and it passes to a classifier to produce a risk score. So for example, if the score extends a threshold like 0.5, we will predict it as a impending failure. For the experimental setup, AAAT was evaluated on a massive dataset from Alibaba Cloud, around 2.7 billion logs from 300,000 servers across 4 months. We also compare it against some several models like SVM, XGBoost, CNN, LSTM, BERT, and Method. And also for the standard metrics, we will use precision, recall, and F1 score. And then for the results show that the TAAT clearly outperform other models. It achieving an F1 score of 52%, which is 10% better than BERT. Also, for the other part, that the log tokenization and TRE are essentially significant important because if we remove that part, with no TRE, we only receive like 44%, and no tokenization, we only receive like 36%. And then for the real deployment part, the AAT is just not a theoretical theory, but it's deployed at Alibaba Cloud. In production, 60% of failure predictions are made more than an hour in advance. The AAT also helped to prevent 55 additional server failure in 1 month, and also saving like 275 VM. This proves that the value of this paper architecture. So for the strength of the paper, the first one is the novelty part. We want to integrate the timestamp with the semantic context to the transformer. Then for the efficiency, the tokenization and time embeddings, it reduces the input complexity and the training time too. And then for the deployment, It is validated in a real-world high-scale system in Alibaba Cloud. Then for the weakness and opportunities, first, uh, the class imbalance. The failure cases are rare, it impacting the sensitivity. And the second one is about the generalization. The results are only shown on the Alibaba Cloud. But how well does the TAAT perform elsewhere? For example, in other cloud provider or other system types. And then the third part is about the interpretability. The model lacks insights into why it makes that predictions. For example, like which type or timestamps most influence the prediction. So for the last part is about the question for the author. I would like to ask three questions. First one is, can the TAAT generalize to other domains like the data centers or for the IoT? The second question is, all the attention weights be used for interpretability? And the third question is, what strategies were tried to mitigate the class imbalance?
Now is our second paper with title, Effectively Capturing Label Correlation for Tabular Multi-Label Classification, which was accepted at CIKM 2024. Our presentation follows this structure: introduction, related works, methodology, experimental results, strengths of the paper, weakness and opportunities, questions for the authors, and conclusion. Now we start with introduction. Multi-label classification refers to the scenarios where a single instance is associated with multiple labels. This is common in real-life applications such as movie genre tagging, where a film might be labeled as both action and sci-fi. In tabular datasets, solving multi-label classification is more challenging due to the complex interaction between features and labels, and the need to capture label dependencies. Existing methods often ignore these dependencies or struggle to scale when the number of labels increase. Prior approaches to multi-label classification fall into two main categories. The first is problem transformation, where multi-label problems are decomposed into several single-label problems. However, they ignore inter-label dependencies and scale poorly as the number of labels grows. The second is algorithm adaptation, where models are specifically modified to handle label interactions. For instance, Cocoa and Simul introduce correlation modeling but suffer from high complexity and limited generalizability. This paper introduces TAMO, which is distinct in two ways. It transforms tabular data into images and employs graph convolutional networks to model label dependencies more effectively. Now I would like to talk about the architecture of TAMO, which consists of three parallel paths. First, the feed-forward neural network path processes raw tabular features using a standard dense network. Second, the transformer path begins by transforming each instance into a square matrix that captures pairwise features interactions. This matrix is rendered as a heat map image. A CNN backbone processes the image, and the resulting feature map is passed to a transformer encoder, which captures contextual relationships across features. Third, the GGN path builds a dynamic label correlation graph. Unlike traditional static co-occurrence matrix, it uses both structural features from the transformer and semantic features from the CNN, which evolves as the network trends. Its paths outputs prediction independently, and these are combined to ensure that all paths contribute to the final decision. Here are the experimental results. TAMO was tested on 7 benchmark datasets from diverse domains like images, audio, text, biology, and video. It was compared with a strong baseline and achieved the highest rank in 71% of cases and second best in remaining 29%. Based on metrics like average AUC, precision, and ranking loss. In terms of scalability, TAMO outperformed other deep learning models in runtime on large datasets, and application studies showed that Removing any components like FNN or transformer or GCN resulted in lower performance, providing that the full integration is essential. Furthermore, using retrained CNNs significantly boosts results and convergence speed. Now I would like to talk about the strength of the paper. This paper is impressive in multiple ways. From a novelty perspective, it is among the first to treat tabular data as images and apply state-of-the-art computer vision techniques to multi-level classification. In terms of technical soundness, it has a solid architecture with clearly defined roles for each component and an innovative dynamic level graph. Each module contributes meaningfully to the final result. Regarding significance, TAMO sets a new performance benchmark in tabular multi-level classification and presents a new direction for combining structured data with deep visual models, opening up cross-domain research opportunities. Despite its strength, TAMO has a few limitations. The most obvious weakness is computational cost. Furthermore, TAMO does not address level imbalance or feature noise, which are common in real-world datasets. However, these limitations suggest interesting opportunities. Future work could focus on optimizing the image conversions process, incorporating lightweight models or interoperability mechanism, and combining TAMO with sampling or feature selection techniques to enhance efficiency and robustness. We would like to raise a few questions for the authors. First, how sensitive is TAMO to the choice of image conversion functions? Would a small change in how the matrix is built impact performance significantly? Second, given the model's complexity, is TAMO deployable in low-resource environments or real-time systems? Lastly, why did the authors choose not to incorporate level balancing or feature selection, especially considering their prevalence in real-world pipelines? In summary, TAMO is a framework that integrates feed-forward networks, image-based transformer, and GCN to improve multi-level classification on tabular data. It leverages powerful tools from computer vision to capture complex relationships between features and levels. Furthermore, TAMO performs well across various datasets and scale efficiently, offering a practical approach for handling real-world multi-level problems. Overall, TAMO bridges structured data and deep learning in a creative way, setting a solid foundation for future research in this space. And that's all for our second paper.
Hello everyone, today I would like to present about continuous personalized knowledge tracing, or we can call CPKT, from CIKM 2023. The author of this paper, as you can see on the screen here, and my name is Minh Bang. Today I will present this paper. About the summary, the presentation is similar to my friend's presentation. I would like to talk about the introduction. Actually, the basic motivation is traditional knowledge tracing models struggle because they treat all students the same and cannot handle long-term learning well. This limits the ability to track each student progress over time. To solve this problem, we use CPKT. This model can continuously adapt to each student's unique learning pace or styles. About the related words, actually the early models like PKT or AFM were basic and didn't personalize, or about deep learning model like TKT or TKVMN. It uses a series memory for all students. It's not personalized. And about a transformer model like SAKT or AKT, improve the predictions, but work apply without personalization. So the CPKT come up solve this problem by enabling continuous and personalized learning. About the methodologies, actually the CPKT builds based on the dynamic key value memory network and adds some three major innovations to support the personalized long-term online learning. The key component is personalized memory slot, unit for each student, personal embedding to capture individual learning style, and the final one is transition-aware stochastic series embeddings. This one helps to prevent the overfitting. As you can see on the screen here, first of all, we receive the prediction request for the student or the problem. Then we read the student knowledge state from the lifelong personalized memories. Then we fit the new interaction data here. We apply the transition-aware stochastic embedding to swap the similar problem embeddings and reducing the overfitting. After on, we update the student knowledge by forgetting and acquiring new information, then write back to the memories. But actually, why is it matter? Because CBKT is designed for the real-world online education system where learning is long-term, dynamic, and deeply personal. About the experimental, you can see here we test on 4 datasets here, and you can read the detail of these datasets on the table 1 here. We also use the SIG baseline and the metric for both task regressions and classifications. About the table 2, actually CBKT can outperform on baseline consistently. Or you, for example, it had the lowest evaluation metric here for this dataset and highest for these datasets, as you can see on the final line. About the application studies, it's confirmed the importance when you personalize and transition aware as well. When we combine together, we get the best performance at the final line. About the table 3, this focus on long-term learning, as you can see on the screen, these values and these values. CBKT perform best for students with long learning history. This one is the trends of the paper. Actually, this paper is strong because it proposes a new, fully online personalized KT model with the level regularization methods called transition aware. The model is well tested on 4 real datasets with detailed analysis. It has great potential for real-world education platform and support long-term adaptive learning as well. We also talk about the weakness and opportunities. Actually, the weakness or the challenge is higher memory and computation cost due to personalization, lack of real-time deployment experiment, and sensitive for noise data. But we also have opportunities because we apply the transition aware beyond education, and we can hybrid the online or offline training. Then we can improve the robustness as well. Some question about the author. We not only provide the questions, but also provide our perspective for this question. The first one, how was CBKT scale in real time for a platform with million students? Actually, I think we can consider lightweight embeddings or share the memory cluster for scalability. And the second question is, can use this transition aware stochastic embedding outside the education? I think yes, because we have similar transition-based behavior appear in another field like healthcare or finance. The final one is, how can CBKT make more robust with the noise data? I think we can use the confident way inputs and denoising preprocessing techniques. So 3 conclusion idea I want to say is CBKT is significant step forward in the personalized long-term KT, and it demonstrates a strong experiment result and practical innovation. Not only that, this opened the new research direction in online adaptive learning, regularization methods, and lifelong learner modeling. Thank you for your attention. Thank you so much.